Alright, so picture this. We're working on a full stack application. You got some code you got to write to your server, and you're using the local host to launch it. You just read about this super ultra secure framework that's supposed to make sure data doesn't leak whatsoever. You're super excited to run it, but when you do, you get this error.
You look all around the docs for why this could be happening, trying different things until you come across a doc talking about HTTPS protocols?
Now I know that HTTPS errors may not be super complex for us full stack web devs, but the point I'm making here is that web dev is way more than just learning JavaScript and Node and launching an app. If you don't know how the internet works, you can encounter similar errors and not know how to handle it. So today I will give you guys a brief overview of how the internet works from the bottom level hardware that runs the infrastructure to your end as a dev. Hopefully this will give you some insight when you're building your next app.
Start, what is the internet? Merriam-Webster defines the internet as an electronic communication network that connects computer networks and organizational computer facilities around the world. In simpler terms, it's a network that connects computers all across the world and allows them to talk to each other. As you know, the internet is how computers share information across long distances. So, rather than sending an important letter to your friend across the country and waiting days to weeks for a response, you and your friend can hop onto a computer connected to the internet and send a letter that will reach him instantly. I wonder why that sounds familiar.
The basic premise of what the internet is and what it can be used for. A network where computers can talk and share information. But how do we connect these computers in the first place? We can't share that information over thin air, right?
Well, not exactly. Unlike radio waves, which can be broadcast over the air, computer data needs a more reliable way to travel long distances. And I want to show you something that'll blow your mind. This is the actual map of the undersea internet cables. These fiber optic cables, some stretching thousands of miles across entire oceans, are what allow data to travel across the globe. When you load a website hosted in another country, your request isn't magically flying through space. It's physically traveling through one of these cables deep beneath the ocean.
A lot of us, myself included, may have thought that the internet was just wireless signals flying through the air. But in reality, the internet is much less of wireless signals and much more like a giant power strip connecting everything together. All the hardware is connected across the globe, and the signals travel across this hardware in pulses of light or electricity.
Oh, take a look. An ePen pal just sent an email from Europe to the US. It just arrived through one of these undersea cables. So what now? How do we get it from the cable to our system?
Well, just like mail arriving at an international airport, data doesn't stop moving at the undersea cables. It needs to be sorted, routed, and delivered into its final destination. First, the data reaches the landing station, a facility where the undersea cables physically connect to the land-based networks. These stations are like the ports of the internet, acting as the entry point that transfer data from the ocean to high-speed fiber optic highways called the internet backbone networks. These backbones are massive infrastructure networks operated by companies known as Tier 1 ISPs. These are companies like AT&T, Level 3, or NTT. They carry data at lightning speeds across countries and continents, connecting major cities in huge internet exchange points, or IXPs. Think of them as interstate highways of the internet, moving huge amounts of traffic in and out of different regions.
Once the email reaches the US, it's handed off to a regional ISP, which is responsible for delivering data to local areas. These ISPs act like the Postal Service, picking up data from the high-speed highways and routing it through their own infrastructure, which includes data centers, fiber lines, and networking hubs. From there, it travels through smaller, localized networks until it reaches your ISP, the one you pay for internet access at home. Your ISP then sends data through underground fiber optic or coaxial cables to your neighborhood, where it eventually reaches your home router. And finally, your router takes the data, converts it into a format your device can understand, and boom, your email pops in your inbox, ready to read.
How does the internet even know where to send an email in the first place? Well, that's where internet protocols come into play. So go ahead and break that down next.
The first thing to understand is that the entire network of cables is really just sending electrical signals and pulses of light back and forth. At its core, all the internet is doing is transmitting tiny, raw data bursts of energy moving at near light speed. But without some kind of system to manage this chaos, that data would be nothing more than random noise, about as useful as dumping electricity into a power grid with no direction. That's why we need rules to structure and organize all this information, making sure it reaches the right place.
This is where two key systems come in: IP addresses and routing protocols. These act as like the addressing system of the internet, ensuring that every piece of data, whether it's an email, a website request, or a video stream, knows exactly where to go.
Let's start with IP addresses, the unique ID assigned to every device on the internet. An IP address is a unique string of numbers separated by periods that tells the network where a specific device is on it. This is like the street address that tells the postal service where your house is. This IP can also be further specified into which port you wish to get the info on. Let's say for some crazy instance you have more than one mailbox. Your port number specifies which mailbox the letter goes to.
And how does this information get across the network anyway? Well, like the highway system, there are rules for how data can travel to and from a device. These are called network protocols. There are two main ones that direct internet traffic. The first one is TCP, or Transmission Control Protocol. Think of it as the system of signs, traffic lights, and traffic controllers. TCP manages how the data travels over the internet to ensure packets, like cargo on a truck, aren't lost in the endless bustle of the web.
Then you have IP, or Internet Protocol. This is just like your Google Maps. Just like how Google Maps decides the fastest route to your destination, IP chooses the fastest route from device A to device B. But data doesn't just teleport from one place to another. It moves in chunks called packets, each carrying a tiny piece of your email, video, or web page. Think of packets like a couch you ordered on Amazon. It's hard to ship the whole couch assembled, so oftentimes it's sent to you in multiple boxes for you to disassemble at home. These packets travel independently, sometimes even taking different routes before reassembling at their final destination.
So we've tracked our data from the undersea cables all the way to your neighborhood. But how does it make its final journey from the street to your screens? Let's break that down.
When data reaches your neighborhood, it's typically traveling what's called the last mile, either through fiber optic cables, coax cables, those same ones that you use on your cable TV, or in some rural areas, copper telephone lines. These connect to that box you might see on the street corner or attached to telephone poles. This data then flows to your home and reaches your modem. The word modem actually comes from modular demodulator, because it converts or modulates digital signals from your device into signals that can travel over those cables, and then demodulates incoming signals back into a digital signal your devices can understand. Next up is your router, which, despite what many think, is not the same as your modem. Your modem connects to the internet, but your router creates and manages your home network. It's basically a traffic director that takes in incoming data and routes it to the specific device it's meant for. That's why it needs to assign local IP addresses to each device in your home. So when Netflix data arrives at your router, it knows to send those packets to your smart TV instead of your printer. Pretty clever, right? But wait, we've talked about the physical journey of the data, but there's something else equally important: the languages and protocols these devices use to talk to each other. And that brings us back to our developer friend with the HTTPS error.
Remember HTTP? It stands for Hypertext Transfer Protocol, and it's essentially a set of rules for how web browsers and servers communicate. When you type a website address into your browser, you're actually sending an HTTP request to that site's server, asking it to send back the web page you want to view. But here's the problem. With regular HTTP, it sends all that data in plain text. It's like sending a postcard through the mail where anyone can read it, everything written on it. Not great if you're logging into your bank account or entering credit card information, right?
That's where HTTPS comes in. The S stands for secure. HTTPS encrypts your data before sending it, like putting your postcard in a locked box that only the recipient has the key to. Even if someone intercepts your data packets, they just see scrambled gibberish instead of sensitive information. And this is exactly why our developer at the beginning got that error. Their ultra-secure framework was trying to use HTTPS, but their local development environment wasn't properly set up for it. The framework refused to run on an insecure HTTP because it was designed to protect data. To fix this, they need to set up SSL certificates on their local environment, basically creating encryption keys that let their code run securely, even just on local hosts. Many frameworks now require this by default because security isn't just for production environments anymore.
There's one more critical system we haven't discussed yet that makes the internet more user-friendly. That's DNS, or Domain Name System.
You see, computers love IP addresses, but humans prefer names we can actually remember, like youtube.com. DNS is like the internet's phone book, translating human-friendly domain names into computer-friendly IP addresses. When you type in youtube.com into your browser, your computer first asks the DNS server, "Hey, what's the IP address for youtube.com?" Only after getting that answer can your browser send its request to the right place. It's a bit like calling information to get someone's phone number before you can call them, except DNS happens automatically and takes milliseconds. So let's put it all together. When you click on a YouTube video, your browser uses DNS to figure out YouTube's IP address, establishes a secure HTTPS connection with YouTube servers, requests the specific video data via that connection, and then that data travels across the undersea cables, internet backbone, regional networks, your local ISP, through your modem and router, and finally to your device where it's decoded and displayed. All of this happens in seconds. It's pretty mind-blowing when you think about it, right? So the next time you run into a web development issue that seems mysterious, remember that there are many layers to how the internet works, from physical infrastructure to protocols and encryption. Understanding these fundamentals won't just help you debug problems faster, it'll make you a better developer who can build more secure, efficient applications. Because the internet isn't magic, it's a remarkably complex system that follows specific rules, and knowing those rules gives you superpowers as a developer.
So don't just take the time to learn JavaScript or Node.js. Take also some time to learn how everything works under the hood as well. It will actually do you some good. For now, like and subscribe, and I'll see you guys later.
Times are tough, with rising costs for food, gas, housing, you name it. It's harder than ever to keep your money where it belongs, in your pocket. That stress, I get it. It's overwhelming. That's why I'm working on Trinity Capital, the ultimate app for learning financial literacy. It's super realistic, with a clean design and built-in lessons to help you master your money. And the best part, it works on any device with an internet connection. Right now, you can test it for free. Join the Discord server, try it out, and help shape the app while it's still in development. The link's in the description, so check it out.